Good morning. Thank you for coming. If you haven't seen any of my talks before, I tend to have graffiti or street art on my slides, and I will today as well. But this is kind of special to me because this is from Oslo. So this is down by the harbor, so it's quite beautiful, I think. So welcome to Secure Programming Practices in C++. I did this talk once before at a security conference, and then they all had fun titles. But since we're not at a security conference, you don't get a fun title, so you get the boring one. My name is Patricia Aas. I'm a programmer. I work on the Vivaldi browser. I used to work a long time ago on the Opera browser. And in between, I was a consultant a little bit, and I worked at Cisco, making telepresence systems. So there are two quotes from Bjarne. C makes it easy to shoot yourself in the foot. C++ makes it harder, but when you do, it blows your whole leg off. But actually, my favorite is the next one. Within C++, there is a much smaller and cleaner language struggling to get out. And that is the part that most people miss about C++. And in the end, we'll get there. But before that, we'll have fun. So this is the agenda for today. And you'll see it several times, and you'll see the underlined thing move down so you know where you are. But first, we'll look at what kind of specs exists. Then we'll look a little bit at undefined behavior, a little bit at surprising compiler optimizations. Then we'll look at exploitability, and that will be like a large chunk of the talk. And then take your vitamins. And then the 8 I'd really rather you didn't, which are my opinions. Okay, so what kind of specs exist? And that was a major part of researching for this talk. I wanted to see what kinds of things you could actually look at. And there are quite a few. But I chose 3, and the first one that is still not sufficiently famous is the C++ core guidelines. So are you familiar with the C++ core guidelines? Yeah? A little bit? Basically, it's a collaborative effort led by Bjarne, and trying to distill more of what we think, or they think, of as best practices in C++. And it is very, very instructive. So I would recommend browsing around a little bit, but it is quite big. Like if we go back, if you try to print it, it's quite large, 328 pages. But still, that's quite small. Considering if we come to the say cert C++ coding standard, which is only for C++, you have one for C as well, which you kind of have to add on. And then you're going close to 1,000 pages. But the say cert C and C++ coding standard is a software coding standard for the C and C++ programming languages developed by the CERT Co-Ordination Center to improve the safety, reliability, and security of software systems. But basically, it's going through different kinds of problems that you might get in and advice on how to get out. But this is the one that I'm going to look at the most. Today, it's the common weakness enumeration. Now, this is massive, but basically, it describes patterns in code that make vulnerabilities. So we're going to look at a bunch of those. So it is a category system. I think it was mostly meant in the beginning to help automated tools, but it is also very instructive to look at. It's text. And so if you find yourself on one of them, then read through, and it has good advice. Okay, so undefined behavior. I talked to some C++ programmers yesterday because I find it kind of funny, because this is sort of like what we would think as the most painful part of C++. But for some reason, C++ programmers love to talk about undefined behavior. I think we're kind of masochistic. It's like the worse it is, the better, really. But for most people, they might not know what undefined behavior is, which is one of the interesting parts of C and C++. So I'll read this, and this is from the spec. So it says, examples of undefined behavior are memory accesses outside of array bounds, signed integer overflow, null pointer dereference, modification of the same scalar more than once in an expression without sequence points, access to an object through a pointer of a different type, etc. And this part is like the fun part. Compilers are not required to diagnose undefined behavior, although many simple situations are diagnosed. And the compiled program is not required to do anything meaningful. And we'll see how easy it is to make undefined behavior very soon. And we'll have one fun right now. So, well, after this slide. But the basic advice I would say about undefined behavior is don't try to reason about it. Most programmers have this tendency to want to reason about it. They'll be like, yeah, but, blah, blah, blah. And it's like, don't. Because it's getting, not only has it always been difficult to reason, but with more and more advanced optimizing compilers, it is getting more and more impossible to reason about it. So just assume it crashes or it's never executed. Don't try to manipulate and depend on undefined behavior. Because if you do, and you probably do, most people do, when you change your compiler, or your compiler version, or your optimization level, suddenly you will break your application. And that's usually how you find out you're depending on undefined behavior. And this is an example, and it is inspired by Shafiq Yagmour on Twitter. His Twitter handle is down there. If you find undefined behavior to be a fun thing, he has a lot of fun tweets about undefined behavior. So just follow him on Twitter. He's a lot of fun there. And this is from Stack Overflow, where he's also very active in C++. But basically, this loop has this delta access here, this access outside of array bounds, which is undefined behavior. If you run this program, it is an infinite loop. It is supposed to go 4 iterations. It runs forever. Because undefined behavior will introduce programs where you end up maybe not doing anything meaningful, because the compiler can do optimizations based on the fact that this doesn't have to happen. But that leads us into the next one, which is compiler optimizations. Because this was a compiler optimization based on something that was undefined behavior. But you can get surprising effects even if there is no undefined behavior. So I'm going to give an example of a compiler optimization causing surprising effects. This was is still a very famous vulnerability that hit a lot of applications. And that is the case of the Disappearing Memset. And it deals around code like this. So basically, you have some function that needs the user to log in. So then you get the password from the user, then you do your operation. When you're done with your operation, you have this password in memory, and you don't like to keep it around in memory, so now you want to zero out this part of memory. And this looks perfectly reasonable, except that the memset is removed by the optimizer because the optimizer views this as a dead store. No one is ever going to read this memory again. There's no reason to write this. This was a very surprising thing that happened to quite a lot of products that ended up having credentials in memory that they thought they had taken away. So yesterday I went to a bunch of C++ talks, and I realized that the done thing, if I want to be cool, is that I should probably show you this in Godbolt. So I never do live demos, so this will be as live as you're going to get ever. So let's see. OK, so I'm not going to try to make it bigger, so that's unfortunate if it's not big enough, because I'll probably mess it up. But if you go and look down here, that's a memset. So that's good, but we have no optimization. So let's go to, there's still some code here, but the memset is already gone. Let's just, there is no memset. Any optimization level, it's gone. So it might look good in debug, and then in release, your password is still there. Okay, let's see. It'll come back. Okay, so if you see on the bottom here, I have some references to different kinds of parts of other. So here you have the SAE, which has two sections, which is related to this. One is be aware of compiler optimizations, which we have talked about, and you should now be aware. And the other one is clear sensitive information stored in reusable resources, and how to do that. But there has been some solutions around this. For people who are used to Windows, I assume this secure zero memory might be familiar. On Linux, this memset _s is implemented some places, but I don't think it is on Ubuntu, at least. And so if you have code like this in your application, go and read these pages. They have workarounds for different kinds of compilers and different kinds of platforms. But this is not a solved problem. So if you have things like this, then have a look. OK, so now we've looked a little bit at those, but it's more fun to look at code. So let's look at exploitability. We're going to go through these 10. Unsigned integer wraparound, signed integer overflow, numeric truncation, stack buffer overflow, heap buffer overflow, buffer underflow, use after free, double free, incorrect type conversion, and uncontrolled string format. And the thing is, one of the things that I find interesting as being a C++ programmer but being interested in security is that a lot of the things that security researchers consider vulnerabilities, C++ developers consider bugs. Because it is generally, the program is not behaving as it's supposed to. What makes it a vulnerability is if you can use that behavior to do something else. So I wrote the code, I put it on GitHub, yeah, well, it's on my GitHub, so you can look at it there. I got some complaints that some of my examples weren't really fair to see, which is probably true, because I'm going to concatenate two buffers like they were strings, but I don't really care about null terminating the strings and things. But you have to fit things on the slide. And on the other hand, you probably wouldn't concatenate strings like this in C either. But I'm trying to prove a point, so. So we'll do signed integer wraparound and signed integer overflow and numeric truncation error first. Now, there's quite a bit of code here, but the code is going to be repeated. So we'll take it a little bit slow the first time, and then it'll be easier. So basically, you have 3 lengths: first length, second length, and buff length. First length is UN max, so this is an unsigned int. All of them are unsigned ints. And we're going to make buffers of these sizes. And the other ones are 256, because I like that number. But anyway, so we want to check, before we copy into buff, we want to check that buff has sufficiently size to fit both first and second. So we add first to second to check that is under 256. Of course, now you see that it's not, but I had to fit it on the slide, so assume it came as a parameter. But if you add first to second, because of, and this is defined behavior, this is not undefined behavior, unsigned integer wraps. And when you add 256 to UN max, the answer is 255, which is clearly under 256. So we go in and we do the copy. This is very often what you will see. Like this is I'll show you another example with, I'll point to it in another example with malloc, where you have the same kind of idea. But the point here is that you are trying to bypass checks in the code by wrapping or overflowing integers or unsigned integers. So let's look at a signed integer overflow. Now this is undefined behavior. So Other things could also happen, but in this case, we're going to go at what happened on my machine, right? So here we have first length is now an int max, and second and buff is the same. We do exactly the same again. Now we add first length to second length. This will overflow. What happens now is undefined behavior, but on all the times I've tested, this number is negative, which is clearly under 256, and we go in and we copy, right? Okay, so then we have numeric truncation error. Now this is really easy to do. So we'll look at that. So first length now is un max minus 256. So we know if we add 256 to it, we'll still be fine. And then we make our buffers again. But now we pull the check for the new length into another variable. And we are going to put it into an int. Now, unfortunately, int does not have room for uint max. And that's unfortunate because this is not undefined behavior. This is implementation-dependent behavior, which is a whole other category of things. But it doesn't really matter in our case because this number turns out to be negative on my machine, which is less than 256, and we go in again. Okay, so those were the fun numbers. And basically, all of the vulnerabilities around this are around things like that. You make a number really big so you can make it really small. And pass checks. Okay. So then we're going to look at overflows. Now, generally, you might start with some kind of signed or unsigned int overflow wraparound thing, and generally end up in something that is a stack or heap-based overflow. Because what you often want to do is you want to write things that you want to do stuff with in this vulnerability. So now you need to write it somewhere. So this is quite a boring one in a way, but it illustrates something that has been a traditionally very common vulnerability. And this is basically just reading random stuff in, not really knowing how big it is, and writing it into your own memory. Now, this is actually two CWEs. If you see that, it's called CWE2 now 121, which is stack-based buffer overflow. But if you look over gets, it got its own number. So 242, inherently dangerous function. I had to jump through some hoops to be able to get this code to compile even. So this is a good thing. So you shouldn't be using it. But anyway, so here you have a stack allocated buffer, and then you're reading random stuff to it that can be much bigger, and then possibly overwriting your stack. And this one is interesting in two ways. We'll do the first one. Let's see. So you have the heap-based buffer overflow. So now you're going to allocate on the heap. And then you're going to copy something that is bigger than what it fits in. And then you are going to write outside of your buffer on the heap instead. But what you will see here also, you have the malloc. And you said size of cart times 10. This is a very typical scenario on where you would also use the integer overflow. So instead of the 10, you will have some kind of integer, and you will get it to wrap. And so the code that is writing thinks that there is sufficient space, but you made the actual allocation small. So that's another typical scenario for those. Yeah. Then we go to the next one. Buffer underwrite underflow. And this is basically going the other way. So instead of writing off the end, you're going to write off the beginning. So you're basically going the other direction. So it's not very interesting, but it's the same idea. So you have some kind of bug in your loop, and then that makes you be able to write all the way. So if you can manipulate the input in a good way, and this is often how you do it, because you have to get your stuff in somehow, right? So generally, you will manipulate some kind of input that the code gets. You first analyze the code, try to figure out what kind of vulnerabilities it is. Then you massage a little bit the input to get it in a certain way to get the code to behave like you want. So that is numbers, and that is strings. That might be files or media files or or protocols where you can manipulate header parameters to basically make the code do what you want. Okay, and these are typical like C++ bugs, right? But they can also be misused. How you will generally see these things happening is you won't generally see them in a regular use, because you will generally get bugs in general use if you have these kinds of things. So here you have a use after free. This will generally cause crashes, so you would have seen it most likely. So where you see these actually turning up is usually where the buffer is only freed in an error situation. So if you can manipulate the program to come into an error condition when suddenly it will do the free and then later use it, now you have memory in a bad state. You have undefined behavior. You can maybe use other things to manipulate it. So this is, and this is the same thing with the, oh, wait a second. So here you have the use after free, and then you have the double free. And the double free is usually introduced in the same way. You only freed it on an error, and then later you do some kind of memory analyzer saying, oh no, this buffer leaked, and then somebody put in another delete. It's an easy thing to happen, right? Yeah. So incorrect type conversion. This is one of my favorite things. You can't do this in other languages. I like the fact that in C and C++, if you really, really want to, you can cast an apple to a pear, and the compiler will say, yeah, I believe you, you know what you're doing. So here we have two clearly unrelated things. And yeah, sure, if you do a hard C cast, you can cast an A to a B. You can do that. It's a feature of the language. Okay. And the good thing, okay, the one thing that you can do with this is, let's say that you had some memory that was allocated for something else, but now you managed to take it over somehow, maybe using it after free or something. Now you can just make an object there of your own choosing, or you can make a manipulated class to manipulate the fields of an existing object with your new pointer, with new features. There's lots of things that you can do that will make this useful. And this is the programming world's version of SQL injection, right? You're basically getting some kind of external format string, and then you're just trusting your input, and you're just letting it go. So in this case, you're getting your format through your command line argument, you're getting your string through your command line argument, and you're calling printf. This is not a very good program, but you could, and now you can just do %s, that's fine. It will put the string in, and then you do a %d, and it will just print random memory. Now, a good thing about things like this is that you can actually get like valid memory addresses and things like that you can actually get print out. You can get information out of the program if you're able to do this, something that you can use to maybe maybe attack it in a different way. So you can get pointer addresses and things like that. Okay, so we looked at a whole, like a little chunk of exploitability, and this is the take your vitamins part. So use your tools. There are quite a lot of tools, because most likely you will have some, all, many vulnerabilities in your code. And a good way of finding them is using the tools that you have. And like I said before, if you're looking for things like undefined behavior, then changing your compiler, using many different compilers, using many different optimization levels, and then running through your test suites, that's a good way of figuring out that you are depending on undefined behavior. But also taking care to look at your errors and warnings. Do instrumentation, fuzzing, static analysis, all of the things that are available to try to find these things and fix them. Then you have paid products too to do static analysis. But many times you will have to do dynamic analysis. Okay, so then you come to my part, my opinions. Okay, so this is the 8 I'd really rather you didn't. And they are inspired by the 8 condiments of pastafarianism, which is great, and you should go read them on Wikipedia. But these are mine. So don't take me too seriously, but seriously think about it. So these are the ones. I'd really rather you didn't use C. I'd really rather you didn't allocate with new. I'd really rather you didn't do math a lot. I'd really rather you didn't trust your external input. I'd really rather you didn't use pointers a lot. I'd really rather you didn't write clever code. I'd really rather you didn't use shared pointer a lot. And I'd really rather you didn't share state a lot. Now, the first four we'll go through a little bit more, and the last four not so much. I'd really rather you didn't use C. And here I can point to the core guidelines, right? The core guidelines has a point on this, prefer C++ to C. Because C++ has very good features that will make it so you don't have to use many of the dangerous features of C. So try to use C++ language and the facilities that are there to avoid many of these situations. And in this case, this is how you concatenate two strings in C++. Don't go trying to copy and make buffers and move things around and use char stars, and just try to avoid it as much as possible, and especially if you're going to manipulate it. Use std string or your own company string, but be safe about it. And also, many people don't know that you can do this in C++ because they learned C++ in the 90s, right? And they're like, I don't really know how you do this. Okay, it is perfectly normal. We can do a perfectly normal concatenation with plus in C++. If you want to read in from standard in or out, you do it with stdc in or stdc out, and you will have things that are properly sized. So don't try to be fancy. Just do it the normal way. Yeah, and this is the one that was buffer underflow before. But instead of making a fancy loop, because basically try to avoid loops in C++. Just don't do that. Any kind of loop. Try to do algorithms. Try to do program like Bjarne said. And this is split up just because it rendered better on the slide. But here you have a lambda. It's called is:. You pass it in to find the first one. It searches from the end, and then when it finds one, which is like in the middle of hello and world, it will erase everything from there until the end. And that was what the other code was doing, but it was kind of hard to tell. So this is more readable as well, and less prone to error. And then if you want to cast, we have casts. This is how we've been casting since early 2000s, so this is the way to go. And these are saved casts. So in this case, we have a Spider-Man and an Iron Man, and everybody knows that a Spider-Man is not an Iron Man. And so we make a Spider-Man, we call him Peter. And then we want to set a Tony pointer to Peter. But Tony is an Iron Man pointer, and it's clear that you cannot have an Iron Man pointer pointing to a Spider-Man. And you can't. And Clang says you can't, with a little nice error, just in like arrow that pinpoints exactly where it is, and says error, static cast from Spider-Man pointer to Iron Man pointer, which are not related by inheritance, is not allowed. So you're going to get compile time errors for casts. I'd really rather you didn't allocate with new. Now, this is very difficult from people coming from other kinds of languages, like Java, for example, to C++, because they're used to always allocating with new. And I'm coming to the point where I think you should practically never allocate with new. You have to have a really good reason to allocate with new. And that's kind of strange for people. So I would say I would prefer if you allocate on the stack. That is like my first preference. If you can, allocate on the stack. It's nice, it will manage your scope. So here we have a stack hero. He lives on the stack. He's very happy there. And his scope will be controlled by the lifetime of where he is. Or his lifetime will be controlled by the scope he's in, which is good. If you have to have something on the heap, then use unique pointer. And here you can say that you can create something on the heap by calling make unique. So there's no new there either. So this is the good thing is you can make code so that you can actually grep through your code for new. So this is an alternative to the one underneath where you're using new to allocate a hero. But the good thing here is now you have a unique pointer on the stack, which will manage the lifetime of your hero on the heap. And it will delete it when it goes out of scope. It is well behaved with regards to moves. And so use unique pointer if you have to have something on the heap. Because even though we don't have garbage collection, some people like to pretend that we have garbage collection, and they call it stack-based scope garbage collection. So basically, you end up with the garbage collection happens at the curly bracket. It's very nice. You don't have to run around deleting your own memory, which also means you won't delete it twice. If you take the handle down with the memory, you also know that you're not accessing the handle after the memory is gone. Yeah, so deterministic garbage collection, we like to call that. And then we have something called make shared. And I have a separate point on I'd really rather you didn't use make shared. But if you have to, then this is how you do it. You can hold a pointer, a shared pointer from the stack or transitively from the stack. So you have something on the stack that owns something that owns something that, you know. But you can also do that with make shared. So still no new here. Okay, and this, I'd really rather you didn't do math a lot. Now this is because you saw earlier we had all of these these overflows, integer overflow and wraparound and these things. And basically, my opinion is that primitive types have no semantics. And what I mean by that is that an int doesn't mean anything. An int is a storage form, but it doesn't have any meaning. You can't say that somebody's age is an int because it doesn't make sense. An int can be negative, an int can be huge. It doesn't make sense. It has no semantics. But it does have actual physical limits, which gives it a lot of problems. So I would say try to reduce the value space if you can. If you're using it for something that has semantics, then give it semantics. And there are facilities in the language to give it semantics, give it some kind of meaning. So I wouldn't use enum anymore. It has its own set of vulnerabilities, so don't do that. But an enum class we have now in C++. String literals can be very useful. User-defined literals are kind of cool, and especially when you can make unicorns with them. I don't have an example of that, but you can look it up. Somebody had an example of that. And then size t. Size t, I think I like. Okay, so let's look at an enum class and why it's cool. So here we have an enum class on top. It's called direction. It has north, east, west, and south. Now, one of the major features with regards to security of enum class, it has no automatic conversion to int. So there's no way to compare two enums that are different enums but have the same value connected to them. So if here I've actually assigned them to car just to show you that you can. But let's say that they were 1, 2, 3, and 4. If you had another enum that also was 1, 2, 3, and 4, they would not be equal. And that is one of the things that I find most satisfying with code like this, that I know that it is an actual right one. It is type safe type. So use enum class if you can. But if you want to print it out, there is a way to make it printable, because if you try to print it, there's no automatic conversion again. So you actually have to figure out how you want to print it. And so it has this stream operator to do that. And then this will write NEWS. Okay, string literals. String literals are kind of cool. I like them. I would probably, in my experience, you don't write a lot of strings around in your code. The only place that you write a lot of strings in your code, hard-coded lots of strings, is generally in tests. But in tests, this is kind of annoying. And so this is a very nice way of, let's say that you have an array of inputs that you're going to go through. You have an array of outputs you want to go through. OK, maybe this is a better way. It's very clean. You just say Spider-Man and this lowercase s for all of them. And then you loop through them. You can put this in the loop, but then it didn't fit very well on the slide. OK, so we have user-defined literals. And the one thing here that you see that I didn't mention, actually, is that we have a for each loop here. So I told you not use loops, but I especially don't want you to use loops with numbers in them. So this has no numbers. It's not counting anything. It's just looping through the collection. You don't have to worry about running off off the end. OK, so user-defined literals. And this is a kind of cool thing. Here you have an H, which is equal to 24_hours, and then you have a D, which is 7_days, and then you try to add H to D. And like I said before, normal integers don't have any semantics, but these things do. So when you try to add hours to days, you get a compile time error, because 24 hours cannot be added to 7 days. Maybe you wanted that, and you can make that. But I can also show you how this works. So how you make a user-defined literal is that you make a struct. So these are two structs. They have an unsigned long num. And then they have this explicit constructor that sets the num. It's not very special. And then you make this quote operator, which gives you the suffix that you, so it's like 24_hours. So this is how you make it. And it will make an hours object, and the other one will make a days object. So if you wanted to make it possible to add days to hours, and you can make functions that could do that, right? But if not, then it's not possible, and trying to do it will give you a compile time error. So this is a way of giving semantics to numbers instead of using raw numbers in your code. Because having numbers is a vulnerability, right? It's a way of getting vulnerable. So trying to reduce where you use ints and unsigned ints and all sorts of raw data types that don't have any semantics, and instead try to use things that have semantics. These are my personal opinions. OK, so use size t for sizes. This has been a little bit controversial for some people, but I'm coming to the conclusion that I like it. So if you're going to have something that has the number of elements in the collection, then the normal thing now is to return a size t. One of the things that is unfortunate is it is platform-dependent size and 64-bit, 32-bit dependent, which I don't like. But it's pretty good. OK, so I'd really rather you didn't trust your external input. And this is not so easy, because it's not necessarily that you realize what your external input is, or where you're getting it in. And it's not necessary that you know that you're not sanitizing it properly. So this is where your fuzzers come in. It's a very good way of checking that you're handling your external input correctly. From static analysis, they have this concept here that they call taint. So the idea is that the external input that comes in is considered to be dirty somehow. And anything it touches, anything it's given to, becomes dirty. And so this taint will spread into your program through your interfaces as long as this thing is passed. So the idea here is to stop the taint as soon as possible, to to sanitize it, maybe move it into something else where you're doing limit boundary checking, if you're doing, maybe changing it to a totally different thing, but doing it as soon as possible when you get it in. So this is trying to stop the taint. And you have many different things. Like you have command line arguments that we saw because it's easy and it fits on the slide. But you have like things like protocols, you have size fields and headers, and they can lie, right? It doesn't have to be the right size. If someone can craft a file and give it to you and lie about the size of the body and make you allocate more or less or copy more or less, because they can see maybe in your code that, okay, but here they're going to add a little bit to this. So if I make this number this big, then they're going to wrap around. But they're going to believe that it is this big, and they're going to copy my entire payload into their memory. Because this is the whole idea of vulnerabilities, is trying to make the program do your work. How can I manipulate their input to make them do what I want? This is related to I'd really rather you didn't allocate with new. And this is also a little bit controversial, but I would actually say I'd really rather you didn't use pointers a lot. And the reason for that is that a C++ pointer, or a C pointer, doesn't have any good semantics, in my opinion, again. Because it could point to an object of this type, it could be null, and it could just point to random memory. You don't know what it points to. When someone gives you a pointer, you don't know. It's like you can check it for null. Yeah, that's great. Okay, now you checked it for null. Now you know it's not null. But you still do not know that this thing points to an object that A is there, 2 has not been deleted, because you have to understand that this is like, yeah, the object might be deleted, but it might still be there in memory. It's surprisingly fun in C++ how you can actually call methods on deleted objects and get away with it for a while. Okay? So I'd really rather you didn't use pointers a lot. And then I say a lot because sometimes it is fitting, but really think about it, because this is not a good way to access memory, in my opinion. I'd really rather you didn't write clever code. And the reason why I said clever is because sometimes you think like, oh, this is really elegant, and I did this thing, and blah, blah, blah. But the thing, as the more clever it is, the more, and when I say clever, I mean generally it adds complexity, or it makes it difficult to read, so that people, you know, had to be really smart to understand what this thing does. But the more clever it is, the harder it is to find bugs. The harder it is to fix bugs, or the easier it is to introduce bugs. Because you write the code now, and it's like perfect, but then somebody has to do a little feature, adding a feature here and there, and all of your assumptions are blown away, and they end up introducing vulnerabilities in your code because they didn't understand it. That's not their fault. It's not nobody's fault. But try to make it so that you're thinking about who's going to read your code afterwards. Try to make it, don't write the most clever code you can. Somebody had this quote that said that to debug, you have to be smarter than, how was that? Twice as smart or something than to write code. So if you write the cleverest code you can, you're not smart enough to debug it. Something like that. I don't remember. But basically, just try to keep it as simple as you can, because this is where vulnerabilities can creep in. I'd really rather you didn't use shared pointer a lot. Now, this is, I think most C++ programmers agree with me on this. A lot of new C++ programmers do this because they come from managed memory languages, and they don't really know how to manage memory in a C++ way. I would rather that you try to figure out how C++ programmers usually do this, because first of all, C++ programmers won't like you if you don't manage your memory well. Because this is like one of the central things for being a C++ programmer. This is like, if you don't do this well, nobody will call you a C++ programmer. We are extremely careful about our memory. We have like this little piece, it belongs to this thing, which is here, and who has the lifetime, and the lifetime is this, and It's ridiculous how much C++ programmers can tell you about every single byte they allocate. It is a fascinating thing. But with shared pointer, the idea here is that you have a reference counted thing. Now, it might feel like, oh, yeah, but this is basically garbage collection, right? It's like we count up and we count down, and at a certain point, it goes away. First of all, a shared pointer is not garbage collection. It suffers from all of the same problems that these kinds of reference counting systems have. You can have a circular thing, and then it just stays in memory. But also, it is proof. You have no idea what you're doing with your memory. And so a C++ programmer will see shared pointer all over your code, and they'll go like, I don't think this code is very good. So I'd really rather you didn't do shared pointer a lot, because then you have to deal with your memory. You have to be explicit with your memory, and you know who allocates it and who is responsible to deallocate it. I'd really rather you didn't share state a lot. I used to say here, I'd really rather you didn't use threads a lot, but I changed my mind. Because you can use threads, and especially if you have some kind of high-level API, which is sort of like jobs. But having threads that manipulate shared state is asking for trouble. Asking for bugs that are really, really easy to trigger. Because again, like you saw these vulnerabilities, they're trying to manipulate your program to do something bad. And in this case, they often do manipulations where they are trying to introduce race conditions so that they can do something. And this is about manipulating your program. Sharing state is basically making the manipulations, introducing a lot of different ways that they can manipulate your program. So that is my last, or my really rather you didn't. So what should I remember from this presentation? Because it's a long presentation, and you might not remember anything. Well, I'd really rather you didn't use C. If you don't remember anything else, then do that. Learn some modern C++ instead. Because it is a beautiful language. Inside of C++, there is an island of goodness. And that is how we like to program in C++ today. So don't write C in C++. Thank you. So are there any questions? Yes?
How would you approach the point of not writing very clever code in code reviews?
How would I approach not writing clever code in code reviews? I guess, okay, when this is an analogy. It's a nicer analogy than the XKCD. Because when I wrote my thesis, I had two people reading my thesis, and they had it on paper, and they gave it back to me on paper. And if I had a paragraph where they both corrected a lot, both in the same paragraph, and it was a long thesis, so there's like whole sections nobody touched. But if they were all like writing a lot on one, that was a bad paragraph. I didn't even care about the corrections. I basically just said, okay, throw away that paragraph, we're gonna write that whole paragraph again. So if you see a lot of focus being paid to very small chunks, it's a smell. You don't really have to pay attention to the comments, really, because if there's a lot of, then they're not really useful. It's basically saying, okay, take this out, how can we write this in an easier way? Because it's clear that people got stuck here trying to get it. So does that make sense?
Yeah, but I was kind of thinking it the other way around. When you actually see a new patch coming in that you feel that it's too clever for its own good, and you would warn the author about it.
I think that's,
You would be the reviewer of some of the clever code.
I mean, oh yeah, yes. So if you are the reviewer, how would you try to communicate the fact that you felt it is clever? Clever here is not a really nice word, is it? Okay, maybe you should say clever because it sounds good. No, I would say that you found, because it's much easier to, instead of saying you did something wrong, you can say something about yourself instead. So you say, you know what, this section I found it really hard to understand. And maybe you can simplify it a little bit or something, because I had trouble understanding what it did. So basically then, the person can think that, yeah, well, he's not very bright, but okay, I can dumb it down for him, But at least you're not offending anyone and you got your point across, right? Yeah.
That's a great idea.
Okay, any more questions? Okay, well, thank you. There's, you should put green in the box, of course, and there's some Vivaldi stickers and pens over there, so grab some. Thank you.